Okay, I'd like to spend our lecture today to continue with our examination into methods. So up to this point, in our last lecture, we had really taken a lot of time to define methods and how they differ from variables, how they differ between classes, how classes and methods kind of interact with one another, how methods are contained within classes, and then classes are contained within packages. Well, today, I want to focus on us actually designing our own utility class. And so utility classes typically have nothing but static methods. We'll talk about that in just a moment. But up till now, and including for the rest of this unit, we're going to just focus on static-based methods. And static-based methods in Java are commonly used to create these utility classes. So a quick overview is that what is a utility class? What are static methods and static fields? We'll talk about designing a utility class, implementing a utility class, designing a tester class, and then finally, how to improve a utility class. So, improving our utility class. Excellent. Okay, so the question is, what is a utility class? A utility class, also known as a helper class, is a class which contains just static methods. It is stateless and cannot be instantiated. So it contains a bunch of related methods so that they can be reused across our application. So a utility class and a main method, a utility class is not typically an application class and therefore does not usually have a main method, right? It's really designed to be used by other classes. So the value of a utility class is that, so a utility class is an example of how Java is an extensible programming language, right? We talked about what that means. It means that we can constantly keep adding more and more code to it so that other developers don't have to work on the same problem that I just solved. Or I don't have to work on that problem across multiple applications, right? Like if there's something that I find is a common process or task that has to be performed, if I can figure out how to solve that task and then put into a class, I can just import that class into any other application and use it. So a good example of a utility class that we've already seen is the math class, right? Because the math class is nothing but static methods that contain, which means it's stateless. We'll talk about what stateless means in a moment, but it's nothing but static methods, which from the class name itself, math, we can call, pass it the data that we want processed, and then it gives back our result. And so regardless of our application, we can write 10 different applications, and in each one rely on the math class to perform some of those mathematical computations for us. So what is a static method or static fields? Remember, a field is just another name for a variable. Typically, fields are in class scope, though. And we also have our static method. So a static method is called from the class scope without the need for instantiating it. Static methods should be stateless, which means that they have one singular behavior. A static field is a variable defined in the class scope that has a single state for the entire class. A state for a field or a variable is what its value is. So when you have a static field, and if it's mutable, if it's not read-only, we've seen those before in math as pi or e. Those were read-only, but we can call from the math class that value state. In the homework assignment, you'll create mutable class fields that represent an enemy position or represent a player position, and you'll actually be able to change that over time. So I just want to illustrate that without the final keyword, the fields are also, they're mutable, they're writable. You can change the value of them. But when you change the value of it, it is of that single value. So it is that for the entire class without having to instantiate it. We'll talk more about instantiation later. But in fact, I want to say we're going to mention it right here when we talk about static methods versus non-static methods. So in the future, we'll learn about instance methods. Instance methods is another name we can define for a non-static method. So we explicitly define when a method is static. If we omit the static keyword, then by default, it's an instance method. And so here, instance methods are stateful, which means that the same method can produce different results or outcomes. It can process things differently based on the instance that is being called from. An example of an instance method that we've already seen is the dot equals method, where the state of the string affects what occurs from that method. So think about it this way. I have a string here, which has the state of foo. Remember, state is a value that could potentially change over time. So in this instance, these are both strings. I have one string literal that is foo, and from that, I can call the dot equals method on. We've seen that. And the dot equals method requires one parameter where we pass in another string instance. And here, if I call on foo dot equals and pass it bar, it's going to return false. But if my string's state is bar and I call dot equals and pass bar, so the parameter that's being passed in, the value being passed into the method is the same, but I get a different result. So this is a stateful result, right? It changes based off of the state of my string, whether my string is foo or bar. So this represents an instance of a non-static method. In a static method, if I was to call this method from the class, it always produces the same outcome. Does that make sense? And again, we'll learn much more about non-static methods later when we get into constructors and instantiations. But right now, we will just commit our scope to the static methods, which are defined in the class, and just have the one behavior for one stateless behavior for everything. Okay, so we were talking about designing our own utility class. So suppose that we want to build a dice utility class. So this dice utility class should have a concept of what all the related methods it contains are, or all the related fields. So in our dice utility class, it will be a class that contains a lot of dice rolling methods. So here, if we were to build, say, for instance, games, whether it's board games or dice games or any other type of games that might require a die to be used, we are going to expect that developers can import our dice utility class and use it to roll die. So the idea of rolling a die is kind of stateless, right? We tell the class the method to do something, and it gives us back a result. So this is a perfect example of when we want to design a utility class. So in our implementation goals that we're going to step through here, we're going to want to be able to make a dice.java file, which will represent the utility class. And then to verify that it actually works, we're going to create a dice tester.java file. And so here we're going to step through what are all the considerations that we're going to have to make in order to properly model a die roll. So yeah, we'll step through how to model a dice with randomness, the equal distributions, explain how scaling works and shifting. And then here, when we get to the tester, we'll talk more about what is a computer simulation. We'll simulate roll and die a number of times so that we can get an accurate simulation. Okay, so let's talk about the data modeling process. This is where we should always first start whenever we try to build anything inside of our Java environment. So before we can start implementing a die, let's talk about what I'm going to refer to as six-sided die moving forward is as a D6. So it's just a quicker way of labeling that. Okay, so with the D6, let's talk about the physical object of a D6. What does it have? It has 6 sides, and what is on each of the sides, or what we'll call faces? Yeah, a pip, and it has a number of pips. It can have one face has a single pip, one face has 2 pips, one face has 3 pips, one face has 4 pips, one face has 5 pips, and one face has 6 pips. And it's designed in a cube shape, right, with presumably sharp edges. Okay, so what is the purpose of a die typically? So we use it as a real world object to generate random numbers. What is the range of the random numbers we can get from a 6-sided die? 1 to 6. So, and what is the, okay, so let's talk a little bit about modeling randomness now. So we talked about what it is to use a randomizer in the real world in terms of a D6. So anytime we start talking about randomness, it's important to know that in the computer science world, in the world of mathematics, in the world of the sciences, we call that a stochastic or probabilistic process, right? It's another word for that is non-deterministic. Like a deterministic process is when I do something, I get the same result, right? When I follow my recipe to create a cake, the idea is I can do that process an unlimited number of times and produce a very similar or effectively the same cake each time, right? That's the point of a deterministic process. But there were some things that happen that you want to model that are non-deterministic. It's probabilistic, and that's inherent in the behavior itself. Rolling a die is that thing. Like if I were to create a model for rolling a die, I'm like, well, 3 is inside the range, and I'm just going to put like roll D6, return 3, right? That you could get a 3, but it doesn't quite capture what the actual behavior of a die is, right? One of the interesting things about a real of the phenomena of rolling die is that it is stochastic. It is non-deterministic. There's no definite way to say when I roll this die, it's going to produce this result. There's no collection of if, else, selection statements I can make that's going to generate exactly what I want, right? Like, so if I want to model that, I want to model that with that sense of randomness. And once I do that, once I realize that I have a problem that I'm trying to model that is stochastic, I have to start thinking, well, how am I going to model that randomness? Okay, so here we gave this example already. An example of a stochastic die is rolling a 6-sided die, D6, is a stochastic event because there is an inherent randomness to it. Each time we roll the die, the outcome may be different each time. In fact, we would hope it's different each time. We can roll the same value more than once. We could say roll the same value multiple times back to back to back, but it has to have a likelihood of also rolling something else. So what must be considered to model randomness? To properly model a stochastic property, we have to identify all the possible outcomes and the likelihood of each to occur. So again, we've done that already for the D6. You could roll 1, a 2, a 3, a 4, a 5, or a 6. So the next thing we're going to ask is, well, what are the different types of randomness that there are? And so we'll talk about that after we're done looking into this. So what is the likelihood of rolling any particular value on a singular D6? It's 1 and 6, right? Like, so there's no favored face, right? So when I roll it, the likelihood of me rolling a 1 versus rolling a 2 versus rolling a 3 or 4 or 5 or 6 are all equal. There's no preference there. We call that a uniform distribution because the likelihood of me rolling any singular value or getting any one value from the collection of values I can randomly get is all the same. So if I were to plot that out, and so here, since there's one occurrence, so I have the face of 1, the face of 2, the face of 3, 4, 5, and 6. Well, I have the number of times I could potentially roll it divided by the sum of all possible outcomes. That's what this is. The likelihood of an outcome is equal to the count of this outcome divided by the sum total of all possible outcomes. So if I were to go ahead and on 1d6, oh, not quite what I wanted, plot that out, the x-axis here would be my die face, right? My value of 1, 2, 3, 4, 5, and 6, and my occurrence count for the likelihood would be 1 occurrence for the 1, 1 occurrence for the 2, 1 occurrence for the 3, and yeah, if we divide that out, that's 1 in 6. So we have a 1 in 6 chance for any singular value. And so here, if we want to properly model our D6, we have to ensure that it follows this behavior. How familiar are you all with random numbers or the likelihood of something occurring? Because there's more than one way that you can randomly select from a group of or a collection of things, right? Uniform is just one of many. We'll look at another distribution in the future, and one that you're probably quite familiar with. But if we implement our die properly when we test it, and we should test it to make sure, especially with stochastic processes, you want to test it to make sure it exhibits the real life behavior you'd expect. But if we were to test this in the real world, you'd go ahead, roll the die, and you shouldn't get a particular preference if the die is not weighted. Okay, so how might we design this roll of a D6 inside of Java? Because that's the core principle of what we want to do. So the first thing we should do is look at some of the APIs that we have access to. And in fact, if we look in the math class has a random method. If I actually read what the random method says from the API, we see it's a static method because, again, math is a utility class. We're designing our own utility class. Our utility class can, in fact, rely on methods from other utility classes. So here we have a static method. It returns back a data type double. It's random without any parameters, right? Because this is the method signature. The method signature is just the name and whatever inputs it requires. And then the description is returns a double value with a positive sign greater than or equal to 0.0 and less than 1.0. So effectively, math.random produces a random fractional number that's scoped and inclusive of 0, but it up to 1, but not including 1. So I'll use the mathematical terms to express the range of between two values, the min and the max. We include the min, we do not include the max. And where no value within that range has preference over any other. Thus, the random method exhibits a uniform distribution, which is what we're looking for in a D6. So this seems like an ideal scenario, but it only rolls a fractional number. In fact, let's take a look at what that looks like. Let's go over here. And we've already seen this actually. Let me blow this up. We've already seen this in the first homework. So I'm going to launch an application called JShell that allows me to run Java code right in the terminal. So here, let me do math.random. And here I see I get 0.71. And notice it's all the precision points. It's like 15, 16 precision points. Here, 0.42, 0.3. And I could do this again and again. It's going to give me let's shrink this down some. Okay, let's see. Is it? Okay, perfect. It's going to give me a different value each time. And the value is a very large value. Even though it's scoped between 0 and 1, the number of digits in that random value is very large because it takes all the precision points after the radix point. So the question is, how might you think we can use this random generator, if it's scoped between 0 to 1, to actually represent our die? How might we model that? Is it possible to use math.random to model the roll of a D6? So we can apply a scalar value. So there's two things we can do in mathematics in order to affect a range of values. And again, a range of values is a contiguous set of values starting at some minimal and going to some maximal. So yeah, we can scale a range. So the most common way to scale a range is to multiply, have a multiplicative property performed on it. So suppose we start with 0 to 1 right here. And to illustrate that this works for any number, I'm going to illustrate what happens if we scale the range of our random value by 2, by 3, by 4, by 5, by 6, and by 6, so that you can see what's going to happen. Here, if I went ahead and discretized my decimal points, my radix points, by every 10th. So I go from 0.1, I'll take 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. And since we don't have 1, I'm going to kind of treat the tail end of what I have access to as 0.99, right? And realistically, it would be like 0.999999999 until I get 15 or 16 decimal places back. But we'll just go ahead and look at the first 2 leading 9s in our decimal place. So let's say I want to scale the range. So instead of just having 0 as the leading digit, I could represent 2 options. So imagine with a random number generator, if the goal here in terms of representing the number of outcomes that we're looking to have, that will be the what's on the left side of the radix point. That will be the actual like whole number, the integer number, right, in front of the radix point. And the radix point is the name that we give to a decimal point, but we don't attach the base to it. Okay. So let's take a look. So we'll multiply the entire scope by 2. So what that would look like is if our number was 0.0 and we multiplied that by 2, that would be 0.0. If we did 0.1 it would, by 2, it would be 0.2, 0.4, 0.6, 0.8, then 1.0 at the halfway mark, right? Then 1.2, 1.4, 1.6, 1.8, 1.98. So now if I take these fractional numbers here after performing this multiplication, and if I just cast that into an integer, which means I truncate them, I just drop the fractional part, what you're going to notice is the leading digit, right? The part that we're going to say we can map as the number of outcomes I could randomly select between is going to have a value of 0 or a value of 1. So that means I can map 2 possible outcomes if I scale a randomly generated number by the value of 2, right? Because I can map one outcome as outcome 0 and the other outcome as outcome 1. And my likelihood of that is just, it's a uniform distribution. So it's a 50-50% outcome of whether I'm going to get a 0 or whether I'm going to get a 1. Let's see what happens if I multiply by 3. You're going to see it's going to be a very similar thing. If I take my values that are up to about 0.3, it's going to produce a set of values that still have a leading value of 0. If I get to this block of decimal values and multiply by 3, it's going to give me a leading value of about 1. And then suddenly, if I get to this block, it's going to give me a leading value of 2. If I truncate, so I just have the leading digit, right? If I just have an integer value, it's going to give me an opportunity to have either a 0, a 1, or a 2, right? So 3 possible outcomes. So what you should see here, and again, if we continue, we got leading values of 0, 1, 2, and 3 on range 4. On range 5, it's 0, 1, 2, 3, and 4. And then finally on range 6, it's going to be 0, 1, 2, 3, 4, and 5. So the value of the scalar number represents how many possible outcomes could I map if I were to represent the resulting random number as an integer, starting at the value of 0 and going all the way to whatever this ranging, the scalar value is, minus 1. So if the number is 2, I get 0, 1. If it's 3, it's 0, 1, 2. If it's 4, it's 0, 1, 2, 3. If it's 5, it's 0, 1, 2, 3, 4, right? Because that's still 5. I'm still counting 5 digits on one hand, 5 possible outcomes, but we start counting at 0. Does this much make sense, everybody? Yeah, and so think back on the zombie. We wanted 4 possible outcomes: the outcome of moving up, the outcome of moving down, the outcome of moving left, and the outcome from moving right. So we did math.random, as you might recall, and then we multiplied it by scalar value of 4 to produce one of 4 outcomes. And then after that, we truncated the fractional number because there's 16 digits. Like if we were checking for equality, we probably never get the same random number twice, or it would happen very, very, very rarely. So when we know the number of outcomes, you truncate the fractional, but you'll get a uniform distribution because there's an equal number of values between 0.0 and 0.1, and 0.1 to 0.2, and 0.2 to 0.3, 0.3 to 0.4. So when I'm showing you this, the makeup here, understand there's an equal amount of distribution between all those, which means that the uniform distribution is going to be, when you expand this out, is going to be the same. So that's, I wanted to highlight this. There's an equal count of numbers between example values listed above, so that you know if there is, for some reason, an instance where this only has 2 values in this chart, it's actually an equal number of values when we mathematically do it, because that just means that this isn't evenly divisible by 5 or by 10. It's not evenly divisible by 10, which is the number of selections I decided to publish. So in these instances, like when I'm showing thirds, I'm going to have some instances that show up 4 and 1, but this is such a small sample, it doesn't illustrate that this is in fact a uniform distribution. Okay, so this represents how we could potentially get 6 different outcomes. What value for our D6 would we want to apply as our scalar value? 6, right? Okay. Now the question is, when we roll a D6, the value that we get from a range 6 is going to be 0, 1, 2, 3, or 5, right? But when we roll a D6, it's going to be 1, 2, 3, 4, 5, or 6. So the second approach we can do when working with random numbers is we can shift the entire range of values either to the left or the right. We do shifting using addition. So again, think of it as this way. If we want to shift to the range of values to the right, we would add to the range. So if my range is between 0 and 1, and if I add 1 to everything in that range, well, then effectively my new minimal is going to become 1, and my new maximum is going to be 2. If I want to shift all of the range of values to the left, then my new minimum is going to become -1, and my new maximum would become 0. So for the instances of modeling in a D6, if I really wanted to represent a roll of 1 to 6, all I have to do is take the new scaled range from 0 to 5, add 1 to whatever the result is. And if it was a 0, then it becomes a 1. If it was a 2 that I randomly had pulled from that scope, if it was a 0, it would become a 1. If it was a 1, it would become a 2. If it was a 2, it would become a 3. If it was a 3, it would become a 4. If it was a 4, it becomes a 5. And if it was a 5, it becomes a 6. So by shifting everything over, it still gives me only 6 possible outcomes, but now all those outcomes have shifted to the right by 1. Does that much make sense? So, but the idea is we have to apply our scalar first to rescope our range from between 0 to 1 to 0 to the number of outcomes. We truncate the fractional component because we want to map a outcome to a integer count, starting at 0, going to all the way to the numbers we have. And then if we need our actual value to be meaningful numerically, like in the case of the zombie game, the value didn't really matter. We just used it to represent going up or down or left or right. We represented the unique ID for a particular outcome to occur. But for modeling the roll of a D6, we're actually using the value we're producing as part of the model. So we're going to shift it so that it actually represents a roll between 1 to 6. So does everyone understand the concept by which we will represent our stochastic process of rolling a D6 die? Okay, so then let's move on and talk about, okay, the mathematical expression then for modeling our D6 randomness would look like this. We would have our random number between 0 and 1, not including 1. We would scale it, we'd apply our scalar, and then we'd apply our shift. So let's use our top-down stepwise refinement to actually start building out this class. My top statement, we're going to build a dice library, a utility class that contains dice rolling methods. And for our purposes here, we don't try to build all the methods we want at once. We start with a singular method, and so and we'll grow out our application. We want to make sure our singular method works. After we've tested it, then we can add another method to it. So for our dice utility class, let's focus on rolling a single D6. We'll use our functional decomposition in line with our refinement process. And effectively, this is what we should get when we roll a D6. We're going to generate a random fractional number between 0 and 1. We'll multiply it by the number of possible outcomes. We'll cast that fractional number into an integer to drop the radix point. And then finally, we'll add 1 to shift the range from values from 0 to 5 to 1 to 6. Oh, yeah. Okay, so let's actually start building this out. Well, actually, that's completely built out. So this is what that would look like. I would have my class here, public class dice. I would create inside of there a static method, because again, these are all supposed to be stateless methods. These are stateless function methods that we're doing because they're going to return back some data. They don't require any input. Here, we're going to produce the random number between 0 and 1. Here, we're going to multiply by the number of outcomes, which is going to be 6 possible outcomes on a 6-sided die. Then we're going to cast that into an integer to drop the fractional component. And then after we cast it to drop the fractional component, we will shift it. We will add 1 to it so that our range becomes 1 to 6. When we get that, we will just store that into a die variable so that we can apply a name to that. And then we'll just return that. Excellent. Does anyone have any questions in terms of this source code here? Let's go into here. Let's create perfect. Let's create a dice class then, which will represent our utility class that we're designing. There we go. And we will save that. Okay, so it's not, once we've spent, so we spent a lot of time talking about our data model for a D6. And then after we've spent that time and then looked at some APIs and then plotted out how we'd actually model it, the implementation was super simple, right? And when we read the implementation, it's very evident in how it followed our mathematical expression, how it followed our data model. But it's not, we're not done yet. Even if we're not building an application from this D6, even if this is a utility class that isn't designed to run in and of itself, we still have to test it to ensure that what our expectations are, that our data model, the way that we're synthetically simulating the behavior of a die inside of our application, is incongruent, that it is that it mimics, that it emulates the actual role of a die. So after I'm done building my utility class method, I can't just execute it and test it, because again, utility classes rarely have a main method because they're not designed to be applications. So what we're going to do is we're going to create a simulation application. We're going to create a D6 simulation application. This will be a class that will make use of our utility class to roll a D6 6 million times. Now, a simulation is a very common application to build in the software world, right? So let's talk about what it means to be a simulation app. In this instance, a simulation app rolls a D6 many times, recording each roll to check if its probabilities are similar to a real D6. Simulation should synthetically reproduce the behavior of authentic observations. We've probably all been watching a lot of simulations with the hurricane that has just recently hit off the coast of Florida, right? That's enough. That is a synthetic model built off a lot of numerical data that goes into a representation of all of the meaningful measures of the ocean to try to predict how the storm is going to move across time and space. But the model that you see, that's the forecast, is not real, but it's based off of the observations of real world phenomena. And if it's a good model, then the projected pathways, right, the synthetic paths that are simulated inside of a computer will then tell us information about what will happen in the actual real world, what will actually happen with the real storm. Now, not all models are correct, right? In fact, rarely are all models fully complete, but they just have to be good enough to give you insight in the phenomena that are happening around you. So whenever you talk about simulations, a big thing about what we do in computer science is build simulations, whether we realize it or not. So it's an important concept to think what a simulation is what we've been doing. We've been simulating lots of things, sometimes imaginary, sometimes real. So if we wanted to check and see if the mathematical probabilities of a real D6 was 1 in 6, how might you do that? Let's talk about how you would actually test this. If you had a D6 and I said, prove that this is a 1 in 6, not by math, but by behavior. You would pick up the die, you would cast it, and then you would record what the value is, right? And maybe you would have 6 different counters, the counter for if it was a 1, a 2, a 3, a 4, a 5, or a 6, and you might roll that a lot of times. And because you're trying to look at the probabilistic behavior, because if you just roll it once, that doesn't give you enough information. If you roll it once, you might get a 3, and you're like, yeah, it gives me a 3, and nothing else. So then you'd roll it again, maybe it gives you another 3. You roll it again, then it gives you a 2. So in order to build up to see if the likelihood, because again, it's stochastic, so you have to observe stochastic processes over many different trials. And then it illustrates a behavior, a distributed behavior. We're looking for a uniform distributed behavior. And so suppose I asked you to roll a D6 6 million times. How many times should you roll a 1? Yeah, like 1 million times, right? And how many times should you roll a 2? Approximately 1 million times. And a 3 should appear approximately 1 million times, not exactly, because again, it's stochastic. But if it's truly uniform with a trial size at large, you should get approximately about 1 million per side. Now, if I asked you to do this in the real world, how long might it take you to roll a die 6 million times? A while, right? One of the advantages of simulating behaviors inside of a computer is we can do it much quicker and cheaper, right? We can simulate. So if this die actually exhibits properties that we'd expect it to, then doing computer simulations allows us to like kind of predict the future, right? It's cheaper to do these experiments, and we can do larger trial runs than what you can do in actuality. This is one reason why computer simulations are so useful even in traditional sciences like chemistry and biology and physics, because it's cheaper to run simulations, narrow it down to the most optimal result, and then you take the optimal results and actually try to put it in production. So if it's a chemical compound, you narrow down what the actual compound should be digitally, and then you try to manufacture it. So it's just an illustration that computer science has affected every domain of every profession, and in a very positive way, right? It makes things cheaper and quicker to develop. Okay, so here, what we're going to do is our simulation app is going to set up our initial data model to count the occurrences for each die outcome. Then we'll repeat many times, rolling a die and incrementing the appropriate counter, and then we'll print the count of occurrences for each die phase. So that's going to be my top-down stepwise refinement that I'll use for my simulation app. So with that said, why don't we start implementing? I'll take my commented code, and I'm going to put it into a dice tester class. I'm going to put in the main method. It's going to be a pretty simple class here. here, I'm going to set up my initial data. My initial data is going to create 6 different counters: counter 1, counter 2, counter 3, counter 4, counter 5, and counter 6, which is going to count the frequency of each of those occurrences happening. So I'm going to initialize those values to 0. Then here, for the second thing I want to do, I'm just going to create a for loop. I say I'm going to repeat this process many times. I think many times here is about 6 million times, right? That seems like a large enough sample size. And I should be able to see about 1 million times for each of my counters should be incremented. So for 0 to 6 million, I don't know if I ever showed you this, we could put underscores to act as a delimiter inside of our numbers. We'll increment. Here I will roll inside of my dice class. So notice, to test this, I'm actually going to access the roll D6 method from the dice class itself. I'm going to save that, and then I'm going to use a switch statement. So my switch statement here is going to operate on the case of whatever this die roll is. If it were the case of 1, I increment the 1 counter. If it was the case of 2, I increment the 2 counter. If it was the case of 3, the 3 counter, the 4 counter, the 5 counter, or the 6 counter. And then finally, I will print out the state of each of my counters. I'll print what the die face is, and then the number of occurrences that actually occurred on those 6 million rolls. Is there any questions about how this tester is defined, or is this code simple enough? Okay, so what we'll do here is let's take this. Let us make a Okay, so here I'll go ahead and paste this in here, and let's see what we get as a result. Let's go ahead and compile our code. Yeah. And let's run that. And notice it takes like not even a second to run 6 million simulations of rolling the die. And my results are approximately about 1 million times, right, per face. So what that tells me is that I do have a uniform distribution, which means that this actually simulates what it would be like to roll an actual D6. So I could use my application instead of actually having a physical die to roll, and I should have the same types of results I would expect if this were a game, for instance. And each time I run this, I should have a different set of outcomes here. Sometimes it's a little more than 1 million, sometimes it's a little less, but approximately it's going to be about. Okay, let's talk about improving our utility class. So right now, and one way we can improve it is to talk about modeling ND6, such as, say, for example, 2D6. So right now, our dice utility class, we might want to add another method to it, because suppose we want to roll multiple D6 die. The way that we currently have it implemented, we would have to invoke that method multiple times. Or say, for instance, we wanted to be able to get a different random distribution. Right now, when we roll a singular die, we get a uniform distribution. But what if we wanted to get a normal or Gaussian distribution, a different likelihood of when our values might actually occur? So what we're going to do here is we're going to design a new method that overloads the D6 method that's going to take in an integer argument that represents the number of D6 die that we want to roll. So we'll have 2 methods, D6 without any parameters and D6 that has a singular parameter, but they'll have 2 different behaviors. What does it mean to be normal or Gaussian? I'm sure everyone's heard of that, and I'm sure everyone's heard of the bell curve, right? The bell curve is typically one that talks about a normal or Gaussian distribution. So recall that on a single D6 roll, my distribution is equal for all of my individual values. I'm just as likely of rolling a 1, a 2, a 3, a 4, 5, or 6. But there are a number of random stochastic processes that don't have uniform distribution. They have a Gaussian distribution. You're more likely to have something from the middle, and you're less likely to get something that is one of your outliers, your min or max. right? And so if I were to roll 2d6, that is an illustration of where we no longer have a uniform distribution. Because if I were to take the two values and sum them together, say, for instance, what are the possible, what's the range of values I can have when I have 2d6? It's 2 to 12, right? The minimal value is 2, the maximum value is 12. Let's look at the chart that I posted here. How many different ways can I roll a 2? How many different ways can I roll a 3? 2, right? So I can roll a 2 by rolling a 1 and a 1 on both the die. I can roll a 3, though, 2 different ways. If I roll a 1 and a 2, or a 2 and a 1. How many different ways can I roll a 4? That's right. A 1 and 3, a 2 and 2, and a 3 and 1. How many different ways can I roll a 4? A 4 is 3. Yeah. What about 5? 4 and a 6. And that's the most, right? There's 6 different ways I can roll a 6. If I roll a 1 and a 5, if I roll a 2 and a 4, if I roll a 3 and a 3, if I roll a 4 and a 2, and if I roll a 5 and a 1. What about a 7? So 7 should be 5 different ways, right? Oh no, I'm sorry. 7 is the highest. Yeah, that's 6. So it goes it's 1, 2, 3, 4, 5, 6. So that's a 1 and a 7 is a 1 and 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. So, and then 8 is 5, and 9 is 4, and 10 is 3, and 11 is 2, and 12 is 1. Just a 6 and a 6. Okay, so the idea here is when I roll 2 6-sided dice, what is the most likely value I could potentially get? It's a 7, right? Because out of all the possible outcomes, how many outcomes do I have total then? How many outcomes, if I were to add all the different possible ways I can roll a 2, a 3, a 4, a 5, a 6, I have 36 different outcomes, right? So out of 36 possible outcomes, how many ways can I potentially get a 7? It's 6, right? So 6 out of 36, that's like a 1 in 6 chance. I'm more likely of getting a 7 than anything else. And then you could see, I can then trend towards that middle point. So I have like 5 out of 36 ways to get either a 6 or an 8. But I only have 1 in 36 ways of getting either a 2 or a 12. So I'm much more likely to get a value from the center, those are preference, versus on the ends, on the min and max. There's lots of times when we observe stochastic processes where this is the random behavior we want. This is important. This is why I'm covering this, the idea behind rolling a single D6 versus just 2 D6. Super practical. You've probably done it lots of times, but have you ever considered the likelihood, the distribution, the probabilistic difference between those two different random approaches, those two different random distributions? These are important things to look at when you're modeling stochastic processes. What is the likelihood of each of these outcomes occurring, and making sure you use the same or similar behavior, the one that's consistent with reality. And so if I were to render that into a plot, notice how my distribution looks much different. I'm much more likely to get this peak, and then here I'm much less likely to get these ends. So this, if I were to have a larger sample size of values, this would start to render into what looks like a bell curve. We have such a small amount of values that it looks more like a triangle. Okay, so let's talk about how we might design our overloaded D6 method in our utility class. Let's call this, again, roll D6. That's the entire point of an overloaded method. We use the same name so we don't force the developer to remember more things. But now, instead of having no set of parentheses, no sets of inputs, it will take in an integer input that represents the quantity of D6 die we want to roll. And then as our output, we'll go ahead and talk about giving whatever the die sum is. So our initial data is the quantity that's going to be given to us by whatever the calling code is. The client code will give us a value that represents the quantity. But then for us, we'll have a die sum that represents 0. And to test this, we'll also do a combo text. So we won't just return a sum, but we'll ensure that the sum is correct by kind of recording what the individual roles are and displaying that. So we'll have our combo text be an empty string. And so our algorithm is we'll repeat a quantity number of times the following action. We'll roll a D6. And so we call the other method that we implemented to roll the single D6. We'll add whatever the result of that is to the sum, and then we'll concatenate to our string, our combo text, that particular value for that roll. That way we can make sure it happened X amount of times. Because again, stochastic processes, you have to be able to evaluate to make sure it's exhibiting the behavior you would expect. At the end of that, we'll go ahead and also concatenate the sum to our combo text. We'll print that combo text, and then we'll return the sum. So that'll be our pseudocode that we've developed from our top-down stepwise refinement process. So let's put that into action. Here is going to be an example of the new class. Here is my roll D6, has the same name, but it takes in a parameter. So it's different signature. I'm going to create that combo text, which is an empty string. I'm going to have a parameter, which is my quantity, which is given to me. And then I'm going to create a die sum that I'm going to initialize to 0. Then I'm going to do a for loop that's going to loop a number of times equal to the quantity of die we need to roll. Inside that for loop, I'm going to roll D6. Notice I'm rolling this method here. So inside of one method, I can call another. I'm going to get that die. I'm going to add it to my sum. Then I'm going to also concatenate it to my combo string. And then I'm going to do something interesting here, right? I'm going to check to see if the quantity is not, if the current iterator, so the current value of I is not quantity minus 1. So is this not the last iteration? If it's not the last iteration, I'm going to add a plus sign in between my numbers inside of my combo text. And if it is the last one, then I'm going to add an equal sign. So I can illustrate that this is assigned this other thing. And then afterwards, I'm going to concatenate my sum. I'll print that out so that we can test this. And then I'm going to go ahead and actually return the die sum. So let's go and actually update our dice here. So I'm going to add that new method, that overloaded method. And now we've improved our utility class because now we can roll X number of die. So let's make a new tester class that it's actually going to test this. So for the purposes of this, I'll illustrate we can still call dice.rollD6 to roll a singular die6, but then I'm going to create a for loop that's going to go from 0 to 20 and actually pass that number in. And we can see how big of a die roll that we roll there. So let's, what I'll do here is I'll just go ahead and go to my dice tester and we will update our code here. Save that. Clear this. Let's go to dicetester.java. Let's call this dice tester. And if we do that, notice what we get here is our singular die roll here, which rolls a 2. And then for a for loop, when we pass in a 0, well, it doesn't make sense to roll a 0 die. So notice we get back a result of 0 because our for loop never runs. And we initialize our die sum as 0. So none of that actually works. So that kind of violates the condition of rolling X amount of die. So, but it's important to illustrate that this is what's called an edge case. And we want to test our edge cases such that it gives us an expected result. This is probably an expected result if we tell the computer to roll 0 D6 die. But if we roll the D1, we can see that we just get 2. If we roll 2 D6, we can see we get 6 plus 2 is equal to 8. So the result we get back is 8. In our application, here is a combo text 3, 5, and 1, which is 9. Here is 4 D6, 6, 5, 6, 1 is 18. 5 D6, 66. What this is showing me is I can have 7d6, 8d6, all the way to a combo text of 19d6, where I got 66. So, but the thing here that I want to highlight is the flexibility we have was, instead of just creating a method that rolls 2d6 or 3d6, by creating an overloaded method where we can pass in a count, we can now roll an arbitrary number of d6 and then get back an appropriate result as if we rolled a handful of dice. Excellent. Does anyone have any questions about this? And this is effectively the process we would go about implementing our own utility class. And if I want to further extend this by adding more dice types or different combinations, I could do that, and I would add that all in the same utility class. In this instance, we work at one method at a time, and we add one new method as we see fit. But we could expand this to have multiple methods, as many methods as this class needs to support. That's right. Each of those numbers represents the actualization of a die roll. So if here I did dice dot roll die 15, that's asking my utility class to roll 15d6, sum them all together, and then give me the end result. And guess what? The distribution probabilities are for anything that's 2 or more up. It's actually a normal distribution. So the only time you have a uniform distribution is if you have a single die. The moment you add one extra die, the entire distribution probabilities shift from being uniform flat to being Gaussian. And the way that the behavior actually changes as you add more die is it gets a steeper incline. So you get more and more trends towards the center and less likelihood of getting to the edges, if that makes sense. So like, for instance, if I were to roll 3d6, my chance of getting a 3 or getting an 18 are far less than on 2d6, and my chance of getting in the middle is going to be far higher. So if you want to, so the idea is that if you want a Gaussian behavior, a normal behavior that really trends towards the center and rarely hits something on the min and max values on your standard deviations out, then you want to go ahead and have those multiple constituent components added together, summed together. Excellent. Any other questions? So, well, then that is our lecture today, and that sets me up nicely for the lecture that I'll go ahead and record and have you all watch later, where we will design a game around our dice utility app, the game of craps. So I'll go ahead and walk through from a top-down stepwise refinement all the way to the implementation, again, using functional decomposition. I'll record that and make that available on YouTube. Maybe answer, maybe about lab, actually. What is the best